Okay, so let's get started. So today we're covering section 1.3, which is on finite and infinite sets. Okay. Okay, so whenever we count things, what we're actually doing is defining a bijection from the natural numbers to the set of objects that we're counting. For example, if we're counting chairs, we're going to say 1, 2, 3, right? So whenever we do that, we're actually defining a function. So we need to formalize this with rigor now, okay? And the beginning of this lecture is about formalizing this notion of counting. So let me write down the definition. So definition. So part A, the empty set has 0 elements. So we just define the empty set as 0 elements. Part B, a set S is said to have n elements, or say a set S has n elements if n is a natural number and there is a bijection from n sub n. And this set we're going to define as the set of elements 1 up to n. So if there's a bijection from this set onto S. So this is how we define the cardinality of the set. Okay. Part C, a set is finite if it is empty or it has n elements for some natural number n. And it has n elements for some natural number n if there is a bijection from this set onto the set in question. And finally, part D, a set is infinite if it is not finite, which is kind of a silly definition, but we need to actually define these things if we're going to introduce rigor into this notion of element-wise sets. So a set is infinite if it is not finite. Okay. Okay. So we need to also, it sounds silly again, but this does require proof, and the proof is in the appendix of your textbook. there is a theorem that we need to state before we move forward. This is called the uniqueness theorem. It states that if S is a finite set, then the number of elements in S is a unique element of the naturals. So then the number of elements in S is a unique number in the naturals. And we need to state that before moving forward. Okay. And then also we need to state that the naturals, so this set is a infinite set. And this is actually stated as a theorem in the textbook. Okay, so with these definitions, we can now move forward and proceed to prove some fundamental facts about finite and infinite sets. Okay, now I'm kind of bummed. My other chalkboard did not come in yesterday. It's been like delayed, so I have to erase, but I'm hoping by next time I'll have two, so I won't have to erase so much. Okay, so give you a moment to make sure you have this written down. And now I'm going to. Okay, so let's look at our first theorem that's going to involve some actual proof writing. So this is theorem 1.3.4. By the way, when you're writing your notes, be sure to write down, come on, Cameron. Okay, when you're writing your notes, be sure to write down the associated numbers with the theorems, because in this textbook, a lot of the results will reference previous theorems by numbers, and you'll have to look back through your notes to find out exactly what theorem was used in the proof that you're currently working on. So, what does this theorem state? So part A, so if A is a set with M elements, and B is a set with N elements, and these sets are, the intersection of these sets is non-empty, and A intercept B is not equal to the empty set, so they're disjoint sets, then A union B has M plus N elements. Okay, now technically this theorem has parts B and C, but we're going to focus on part A, prove that, then move to part B, prove that, move to part C, and then prove that. I might omit one of them for the sake of time, but I'm at least prove two of them. So let's look at the proof. or a sketch of the proof, because honestly, I don't know if I'm going to have enough room, but we'll see. So we're assuming that A has M elements and B has N elements, and their intersection is not empty. So by using the previous definition that I just wrote down, we know there's a bijection from the set A to, or from, so before I move forward, well, I'll just write it out. Okay. So let's say F be a bijection of this set. So recall this is the set of 1, 2, all the way up to N. Onto A. And we know such a bijection exists because we're assuming that A has M elements. And G be a bijection of N sub N onto B. And we know such a bijection exists because B has N elements. And recall, this is new notation, so it might throw you off, but just recall that if you have a set, and if you have the natural number symbol with a subscript, say K, then this is the set of 1 up to K. That's all that notation means. Okay. Okay, so we have F and G as our bijections, which give us the verification of these, the number of elements in these sets. So then we're going to define a new function. So next define, say H, and this is going to be a function, and it's going to be a function on this set. So subscript M plus N. Okay. By. So we're going to say that H of I is equal to F at I for I equals 1 up to M. And H of I equals G of I. Or actually, sorry, I'm running out of room over here. And G, sorry, H of I equals to G of I minus M for I equals M plus 1 up to M plus N. Okay. Now, what's going on here? Well, like, why did we define this function H the way that we did? Well, suppose, so I'm going to do a little bit of scratch work right here, and I'm going to erase it after that. So we know that F is a bijection from this set to A, and we know that G is a bijection from this set to B. Okay. Another way of writing this, by the way, would be to write, the notation can be somewhat confusing at first, and for a lot of you, this is the first time you're really encountering rigorous mathematical arguments, so I'm going to try to break it down as much as I can. So this is 1 dot 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 up to m. So F is a bijection from that set to A, and G is a bijection from 1 dot 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 n to B. Okay. So each of these numbers gets sent to a unique element over here, and everything over here has something that was sent to it from over there. Right. So how does H work? So H, we want H to define, so we want H to be a bijection from the set 1 n plus m plus n. We want that to map to A union B. We want that to be a bijection. So this is what we want. Okay. So is H doing that? So first off, is H a function from this set to that set? Okay. Well, suppose, so what's H of 1? So 1, if 1 is less than, so if 1 is less than or equal to m, then H of 1 is just going to be equal to f of 1, which is indeed an element of A. F takes 1 to some element in A. Okay. Dot, dot, dot. What's H of m? Well, that's equal to F of m, which is also an element of A. Right? Because F takes, so I is less than or equal to m, so we're in this case here. So if F at m is going to be an A. But what about what's H of m plus 1? What's that? Well, now I is not less than or equal to m. I is less than or equal to m plus n and greater than n. So we're in this case. So H of m plus 1 is G of m plus 1 minus m. Right? Right there. So we're evaluating n plus 1, so we just plug in n plus 1 where I is. And this becomes, so n plus 1 minus m, this becomes G of 1. And that's an element of B. You see that? So what about G of m plus 2? Well, put a 2 right there. Put a 2 right here. And then you get a 2 right here. And that's also an element of B, right? So now, every time you have an I that's in here, all the way up to m plus n, it's like you're evaluating it at what you're adding. So the first I, it's like evaluating G at 1, all the way down to this I, it's like you're evaluating G at n, right? Like if this is, so that was an n, right? Then this would be G of n, which is indeed an element of B, because G takes all of these elements to that set. Does that make sense how H is defined now?
Yes.
So now that we have H defined, we need to show that it's a bijection. Now, I don't have enough room here, but I'll kind of like walk you through how that would look. We know that H, just like looking at it here, H is clearly going to be surjective with A. Everything in A is going to have a pre-image in this set. And also, everything in D is going to have a pre-image in this set. Right? Once more, it's going to be injective because F is an injection with A. There's a one to, yeah, F is an injection with A, G is an injection with B, and we're evaluating each of those elements in there. You can kind of see it, right? Like why H is going to be a bijection with A union B. Like the intuition should be there. Formally, you'd have to show the definition. Okay. And I'm tempted to do that for you because I don't know if I'll leave that as an exercise to show that that's a bijection. So on your own, show H is a bijection onto A union B. Okay. That's what's left with that. I'll give you a moment to write that down. Okay. So that was part A. Okay, so part B. Part B states if A is a set with M elements, and C is a subset of A, is a set with one element, then A set difference C is a set with M minus 1 elements. Okay, now it seems trivial, but it's useful to note in subsequent arguments that we'll encounter. Okay, and then part C, if C is an infinite set, and B is a finite set, then C set difference B is an infinite set. Okay, so part B I'll leave as an exercise. and we'll discuss the proof of part C. So. And let's just discuss the general idea behind the proof of part C. Okay, so let's focus on part C for now, okay? So C is infinite and B is finite. And then we want to show that under those assumptions that C set difference B is an infinite set. What type of proof technique do you think would be best when first considering this statement? There's three types of proofs, right? There's direct proofs, contrapositive, and contradiction. Of those three techniques, what's your first inclination when looking at part C?
I think a contradiction.
Right, that's my first thought as well. So let's kind of see what happens under that assumption, right? So again, this is just the idea. So C infinite, B finite, and we're also assuming if we're doing a proof by contradiction, that C set difference B finite. Okay. So what do you think? What's your first thought? Right? What do you do next? And we can use something we were just talking about, by the way. Isn't it the case that, so if B and C are finite, then we can say something like this. Then we may suppose B has M elements and I'll call the set A, which is equal to the set difference, has N elements. Right? Like if they're finite, then there is some number that we can associate with them, the number of elements, correct?
Mm-hmm.
So B has M elements, C has N elements, and also, maybe not also, I would say also, what's the intersection of A and B? Oh, by the way, part B, so part A, I accidentally, make sure in your notes that the intersection is empty. I think I might have written not empty for some reason, but the intersection should be empty in part A of this theorem. I said they're disjoint out loud, but I might have accidentally wrote not empty, but it should be empty. So what do we know about the intersection of these sets here?
C.
Their union is C. This union B is equal to C, but their intersection is empty.
Right,
Right?
because it's C, not B.
Right. By part A union B, which is equal to C, has m plus n elements, a contradiction. And that would be, why is that a contradiction, by the way?
Oh, implying it can be summed means that it would be finite, but C is infinite.
Right, right. That is some integer value, which means C has some integer value of elements, but that would imply that C was not infinite, that C is infinite. That's the contradiction. So maybe you should write a contradiction since C is infinite. And that's the general proof idea. Yeah. Just be sure in part A of the theorem that I erased, make sure in the statement of the hypothesis on part A that that is equal to the empty set. The sets need to be disjoint. Again, I said that out loud, but I don't know if I accidentally wrote the opposite of it. Okay. So that's more or less the proof idea for part C. Part B, I'm leaving for you to try on your own. Okay. Okay, so next theorem. So theorem 1.3.5. Theorem. Suppose T is a subset of S. This is part A. If S is finite, then T is finite. Okay. There is a part B of it, but it's an immediate consequence of part A. So we're just going to focus on part A. So proof. So if S is equal to the empty set, we are done. Since T equals the empty set is finite. So if S is finite, then it's either empty or non-empty with some number of elements in it. If it is empty, then that means that T is a subset of it, then T must also be empty, which means that it's finite. So we're going to prove this statement using induction. And also, I didn't cover it in my last lecture. You need to look at the previous section and look at strong induction. Its statement is similar to the induction that we did, but I will assume that you'll be able to read that definition and understand it, or that idea and understand it. And that's the type of induction that we're going to use. So for our base case, Okay. If S has one element, then T is finite since T is either empty or equal to S. So this satisfies a base case for induction on the number of elements in S. So now we have our inductive step. So what we're going to do now is we're going to assume, so for our inductive hypothesis, suppose every non-empty set oh, I almost forgot a line. So at the very beginning, if S is empty, we're done. So right after that, I would say, so we may assume S is not empty. Okay, so back to our inductive set. So for our inductive hypothesis, suppose every non-empty subset of a set with k elements is finite. So that's our inductive hypothesis. Okay. Every non-empty subset of a set with k elements is finite. That's our hypothesis. And next we're going to say let S be a set with k plus 1 elements. Okay. So S is a set with k plus 1 elements. Then by definition, there is a bijection that you can look at. Let F be let F be a bijection of the naturals up to k plus 1 onto S. And we know that such a bijection exists because S is an element with k plus 1 element. S is a set with k plus 1 elements. Okay. And let T be some arbitrary subset of S. And our goal is to show that T is finite. Okay? Okay. Okay, so now what we're going to do is we're going to say, all right, we have two cases to consider, and you'll see after I write them down. So if F at k plus 1 this is k plus 1, is an element of T. So if that's the case, or suppose actually that it's not an element of T first, it'll be easier. So if that is not an element of T, then what can we say? We can say T is a subset of S1, which is equal to S set difference, that element. And that's the set consisting of that one element. That element is in S, but it's not in T. So since this element wasn't in T, we know that if we take that element out of S and call that set S1, T is still contained in there. And that's because that we're assuming that is not in T. Okay. By theorem 1.3.4 part B, the one case that we didn't prove in the previous theorem, where you'll see in a second. S1 has K elements. Now I want to be sure that you understand that, what I'm saying in this last sentence. The last theorem that I erased, part B, said that if a set has M elements and you have a subset with exactly one element and you remove it, the resulting set has M minus one elements. This is a set with one element in it. This is a set with K plus one elements in it. So if you remove that from that set, you have a set S1 with K elements. You just subtract one off of that. Okay? Now, our inductive hypothesis says that every non-empty subset of a set with K elements is finite. This right here is a subset. This right here is an element with a set with K elements. And T is contained in S1. So by our inductive hypothesis, T is finite. I'm going to abbreviate it I, H, dot H. By inductive hypothesis, T is finite. Okay. So that was under the case when the image of K plus one is not an element of T. And now we need to check the case when the image of K plus one is an element of T. So f of K plus one is in T. Okay. Then let T1 be equal to T set difference, the image of K plus one under F. Okay. So I took that thing out of T1. And then notice T1 is a subset of S1, where S is the set where you get rid of that value. Okay. As before, like we said with T, we can say the same thing about T1. So I'm just gonna, instead of writing it all out, I'm gonna say as before. T1 is finite. When I say as before, I'm just stating that the same argument that we used here on T, we can use here on T1 to show that it's finite. Thus, T, which is equal to T1 union, the set containing that element, is finite. And this is by theorem 1.3.4 part A. One point 3.4 part A. So T is finite because why? T1 is a finite set, that's a finite set. And this theorem says that the union of two finite sets is finite. Okay. In both cases, we've shown that T, which is a subset of S, is finite. So we're done. So we satisfied the base case. So all sets with one element have any non-empty subset of a set with one element is finite. So then that's our base case. And then for our inductive step, we assume that every non-empty subset of a set with k elements is finite, which implies that any non-empty set of a set with k plus one elements is finite. And then we're done by induction. Okay, so I'll give you a moment to finish writing that down. Okay. Okay, as a consequence of part A, we have part B, which states that if T is infinite, then S is infinite. Why is B immediate once we prove A?
Because it's the contrapositive.
Right. B is the contrapositive of part A, which they have the same truth values. So we're done. We don't have to do anything for part B. Okay. And actually, I was going to continue going, but I think that that is enough for today. I can split this section into two different lectures, and I think that's probably the best way to do it. So what you need to do, starting from like here on out, I lecture, you follow, you write with me, you listen, go back, watch the video on YouTube, and then also rewrite the proofs. When I write a proof down or a proof idea, rewrite exactly what I did and fill in any of the missing pieces you think you need to add. and then try to write the proof without looking at the notes. So watch twice, write on your own. No, watch twice, write while looking at your notes, write it completely over again, do that maybe twice, and then try to write the proof on your own without looking at your notes. Okay? That's the only way that you're going to start to build up intuition as to how to proceed, right? Proofwriting, especially in analysis, is just by looking at proofs and practicing those techniques, and the techniques are going to pop up over and over again, like similar types of techniques. And you have to write, and write some more, okay? So that will be it